Right. In that guitar string demo that I did, basically we're just demonstrating that you can form a standing wave on a string by plucking it. It typically generates the first harmonic, and that's what ends up creating the tone of the string. And it's fixed at one end, fixed at another end, and you pluck it and it generates the first harmonic wave that kind of looks like this. Very hard to see it on a stringed instrument because it occurs so quickly. If you're talking about 100 hertz, that's 100 times per second, so it's just going to look very blurry to you. But that's what ends up happening for a standing wave on a string. And if we recall the frequency formula that we saw, it was the harmonic number times the wave speed over 2 times the length of the string. That's how you determine the frequency that you're going to get from that particular string. So the length of the string literally determines the frequency. And what you saw is that I manipulated this variable L, and that gave me different frequencies. So what I did was, as I made L shorter, you saw the pitch get higher, the frequency went up. In problem number 1 of the harmonics practice problems, you have a violin string, which you're told is 0.33 meters. And it vibrates at a fundamental frequency of 440 hertz. So that's when you pluck the open string or do something to get it to vibrate. And then they ask, where should your finger be placed on the fretboard in order to cause it to get a frequency of, let's say, 1.33 times higher than that 440. So let's see what that would end up being. 1.33 times 440 is 585.2 hertz. So that's the new frequency we're looking at. And if we basically press somewhere here, that's going to create a standing wave that would be along a smaller length string. So you prevent it from vibrating over here. We have the frequency we want. We're still going to be generating first harmonic here, and we're going to assume that we have the same wave speed here. But we need to find out what that wave speed is. So initially, we have our first note being 440, the fundamental frequency. That is first harmonic, so n is equal to 1 here. So you got f equaling 440, n equaling 1. V is unknown. The length of the string is 2 times 0.33. So, got a little bit of math to do here. But if we just take 440, multiply it by 2, and also multiply it by 0.33, we should get that the wave speed along the string is 290.4 meters per second. So the waves actually go pretty fast back and forth through that string there. And we're going to assume that that's constant because that's a property of that particular string itself. Now what we want is we want a new frequency of 585.2. That's going to require us to press somewhere different on the fretboard. So let's make our frequency 585.2. Plucking it would still get you first harmonic. The wave speed is 290.4. We need to figure out what the length of that string is. 2L. Basically what I would do is I multiply both sides by 2L. And that cancels out it on the right side. And then, if we're looking at this, we can multiply these numbers out. 2 times 585.2. You get 1,170.4 here. And then we're just left with 290.4 here. So dividing both sides by that, so 290.4 divided by 1,170.4 gives us our answer. And what I get is that L is 0.248 meters. So somewhere along there, you're pressing there, you're shortening the string, and you're getting a higher pitch. That's basically the way that you can approach these types of standing wave problems. If you look at number 2, it tells you that you're dealing with a string that has a fundamental frequency of 480 hertz. And it says draw the wave pattern for this string. How much of a wavelength fits on the string? So this is a very conceptual problem here. Here's your string. 480 hertz is the rate that it vibrates up and down And as we have seen before, the first harmonic pattern, you basically could see it when I did it in that lab for you. You see it moving very slow, but you get a very blurry view as things move faster. So it oscillates between this extreme and this extreme. And this is what it looks like. And when you're asked how many wavelengths occur along this string, keep in mind the formula for wavelength was 2L over the harmonic number. So when you do this, the wavelength of this one is 2L over 1. The wavelength is actually twice the length of the string. So a full wave length would look like that. You only have a half of a wavelength here. So this is only 1/2 of a wavelength that is displayed at any given point in time. And so that's kind of the trickiest one of the bunch here. If you are asked to draw the next two patterns on the string, it's always pretty easy because the second harmonic, this is first harmonic, would just have a different oscillation. Sometimes if you could snapshot the string, if you record it in slow-mo, you might see the string look like that, but then at another snapshot, it might look like this. So it oscillates between these two maximums and minimums, and you would have basically two loops. It'd be a very blurry view, and this does display one full wavelength here. And likewise, if you do a lambda, you get 2L over 2 here, harmonic number's 2. The wavelength is actually equal to the length of the string in this one. If you're doing n equals 3, that's going to be 3 loops. And let me try and draw this effectively. If you were doing this in slow-mo, you might see the string look like this, or you might see it look like this. But if you're seeing the blurry view in real time, you're going to get 3 loops here. And so you actually get 1.5 wavelengths. It's always 2 loops per wavelength, then you get another half wavelength here. And when they ask what the frequencies are, based on what you saw in the lab, the pattern is that each of these frequencies is a multiple of the fundamentals. So if we do 480 times 2, I would expect this one to be 960 hertz, and I would expect this one to be 480 times 3, 1440 hertz here. And so hopefully that helps you a little bit more with the idea of what's going on with these standing waves and why does it apply to instruments